Hello everyone, welcome to week 8 of this uh, course Fundamentals of Semiconductor Devices on a live problem solving session.
Hello, sir.
Hello, just 1 minute. So, my name is Mayank Goel and I am a research scholar at the Department of Electrical Engineering, IIT Bombay. And this course is being taught by Professor Digvijay Nath, who is an associate professor at IIC Bangalore. So, for this week, the course plan is MOSFETs, their structure, their operating principle, their IV derivation, graduate channel approximation, substrate bias effects, sub-threshold current and gate oxide breakdown, control of threshold voltage, short channel effects, Moore's law, and CMOS scaling. So this course is every Sunday 6 to 8 p.m. This live problem solving session, and the Google Meet link is this one. So let's start with questions. Like as always, I will be showing you questions, MCQs about MOSFETs today, which will help you with understanding this concept. So first question, what is the primary difference between a MOS capacitor and a MOSFET? MOS capacitor has three terminals while MOSFET has two. MOSFET has a source and drain in addition to the MOS capacitor structure. MOSFET does not depend on MOS capacitor principles. MOS capacitor requires an external bias to function.
Sir, B, sir.
That is correct. The answer would be MOSFET has a source and drain in addition to the MOS capacitor structure. So the MOS capacitor is metal oxide semiconductor. So in the semiconductor region, you place a source and drain pads. So I will get into the exact working of MOSFET after a few questions. So I will move to the next question. In a MOSFET, what role does the gate voltage play? It controls the temperature of the device. It determines the current flow between source and drain. It only affects the drain voltage. It has no effect on the transistor operation.
B, sir. It determines the current flow to the
That is correct. So the gate voltage is the voltage that you apply on the metal of the MOS part, and it determines the current flow between source and drain. And what happens when the gate channel is lower than the threshold voltage? The transistor channel turns on, the transistor channel is off, the current between source and drain increases, the transistor becomes a capacitor.
again, sir. B. The transistor channel is off.
That is true. Uh, and what is the effect of applying a strong positive gate voltage in a MOSFET? The channel becomes depleted, the channel forms due to strong inversion, the transistor stops working, the gate voltage has no effect.
A channel formed due to strong inversion.
That is correct. So, in a p-type substrate MOSFET, what charges are formed during inversion? Positively charged holes, negatively charged electrons, neutral charges, only fixed oxide charges.
A negatively charged electron.
That is true. Okay, so now I will I will show you how exactly a MOSFET works. So basically, the MOSFET structure is basically, so So this is your semiconductor. Let's assume it's a p-type substrate. So this is your p-type substrate, p-type silicon it is. So you have a gate here, oxide here, gate oxide, and then you have a gate here. This is your metal, this is your oxide. So this is your normally MOSFET structure. Met, metal, oxide, and this is your p-type semiconductor. Now to make to make it a MOSFET, what I do is I place my source and drain regions here. So what I do is I make these highly n doped. So these are very highly n doped here. So these would be opposite to what my substrate is. So my substrate is p type. So my source and I have doped the source and drain region would be highly n type doped. So now when you look for current across between this and this region, this is your let's say source region, and this is your drain region. Then when you look for current between source and drain, you see it's n, then a p, then an n plus, then p, and then p n plus. So you will see that there won't be any conduction between this region. But if I apply gate voltage here, I can create an inversion layer here at the interface, oxide and semiconductor interface. So this interface, and due to inversion layer, this will form an n-type channel. This will become n-type because it's inversion layer. So you know in p-type substrate the inversion layer will be n-type, and in the n-type substrate the inversion layer will be p-type. So now I have n plus, then n here, and then n plus here. So now I will have conduction through this n channel. So this is my on state now. So this channel that is formed, that is causing my conduction. So that is called on state. And this is a very thin channel because it's only at the interface. You know, last week you have read MOS capacitors, how small the depletion region is, depletion width is. So that is the depletion width here. The thickness of this channel will be the depletion width of the MOS capacitor. So this is how a MOS traditional MOSFET traditional planar MOSFET works. For years, this has been the structure of a MOSFET. Now there are new designs of MOSFET coming in, such as FinFET and Gate All Around FETs. But traditionally, this has been the structure of MOSFET, and due to this inversion layer, only your conduction is happening, and when this inversion layer is not formed, your transistor is off. Hence, and you know that inversion layer only forms when your gate voltage would be above your threshold voltage. So hence all these answers to the previous question. So now we will move on to correct IV characteristics. How does the ID versus VD characteristic behave as the drain voltage increases? Current decreases with increasing drain voltage. Current remains constant. Current initially increases, then saturates. Current becomes negative.
C, sir. Initially increase, then
That is right. The answer would be current initially increases and then saturates. So now Why does the current saturate in a MOSFET at high drain voltages? Source drain resistance increases, pinch off occurs at the drain end of the channel, the gate cannot control the current, the drain current reaches zero.
The pinch of occur at the drain end of the channel.
That is correct. So you see here, if I keep increasing this channel by, it will affect my channel thickness here, and at certain voltage it it will restrict the movement of electrons further. So that is called pinch off, and therefore you will have a constant current.
Sir,
Yes,
I have just one question is there regarding that picture.
yes,
Uh, if I increase the drain to source voltage,
yes.
then sir, the inversion will be more.
No, your inversion is coming from your gate voltage.
Oh, gate voltage. Okay, okay. No, no. Actually, sir, pinch off is occurred due to the thickness of the channel is lower.
So pinch off basically, so so your transistor is on now. There is a you have availability of negatively charged electrons here. So
Yes, sir.
when you are applying your so when you are applying a voltage on the drain, so there will be a movement of currents from this channel, right?
Yes, sir. Yes, sir.
But but this drain current will also but this drain current is also affecting the interface at this region because of your gate, and because it will reduce the effect of the gate at this region. So
Okay.
after a certain point, there will be a limit of how much electrons can go through this region, because there won't be any more electrons available for movement.
Okay.
So your current will
But,
saturate
but
your
sir,
so your current is
but
dependent
sir,
on
influx is
what is saying.
actually, sir, you are placing. Yes, sir. You are placing source and drain are in N plus region, na? Highly doped region.
Yes.
So basically, huge number of carriers is available.
No, huge number of carriers are available here, but not here in the channel. Channel, the number of carriers are
Okay, okay,
fixed.
okay, okay, okay.
Your current is
Channel
dependent.
arts are created due to.
Your current is dependent on your current
Sir,
density, electron density.
okay, okay. Sir, I just want to know that channel is formed due to the inversion effect of gate voltage. Yes or no?
Yes. So
So, sir,
last
if we
class,
increase,
in last class, you studied that when you give, if you're in the metal part, if you have a voltage higher than your this threshold voltage, then the inversion layer is formed in your substrate at the interface, and that inversion layer is fixed at 2 phi f.
yes, yes, sir.
So
Strong inversion.
yes, in the strong inversion, the inversion layer is fixed at 2 phi f. Even if you increase the gate voltage further, it won't increase the charge density in the inversion region.
Okay, 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 sir. Okay.
Does that answer the question?
Yes, sir. So, sir, as per you, sir, if we increase the furthermore gate voltage, no effect is there. Channel which is fixed, and if I increase the gate potential, the maximum amount of current transfer from source to drain is also depend upon the width of the channel. So it is repeated. That's why pinch off is occur.
Yes, so pinch off is occurring at actually this point, this region, not the whole channel, but at this
Surface.
region where your drain
Okay,
is
okay,
meeting your channel, because
okay, okay.
there you will have the effect of your gate as well as your drain. So if
As
you
I said, surface.
yes, so if you increase your gate voltage further, your pinch off point will also increase.
Okay, sir.
So next question: what is the relation between gate voltage and threshold voltage for the channel to be formed? The gate voltage must be less than threshold voltage. The gate voltage must be equal to threshold voltage. The gate voltage must be greater than threshold voltage. The gate voltage can be any value.
Answer can be both, sir, equal and greater than. Equal will be the least condition.
Yeah, so the main answer would be it should be greater than threshold voltage. So
Okay, 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 sir. Okay.
equal, you might or might not have. What mathematical approach is mentioned to derive current voltage characteristics? Complex calculus, gradual channel approximation, statistical analysis, quantum mechanics.
Sir, gradual channel approximation.
That is correct. So we are doing an approximation to help us derive current voltage characteristics. So the gradual channel approximation assumes that the variation of potential in which direction can be ignored along the channel, perpendicular to the channel, in the substrate, in the air.
Sir, perpendicular to the channel. I don't know, sir. This answer.
So the answer to this is along the channel. So we are assuming that perpendicular to the channel, there is a huge variation in potential due to your MOS structure. So depletion width, you know how much variation is there in the depletion width, but in the along the channel, like in the perpendicular region, this is the perpendicular region. There will be a huge variation in potential due to this MOS structure, but along the channel, we assume that the variation of potential is very slow between the drain and source. So the variation will be coming because of voltage difference between drain and source. But we also assume that the channel is long enough that we can assume the variation to be very very slow, and we can neglect it. So we only have to do calculations for this region. So it becomes a 1D problem instead of a 2D problem. So which of the following equations describes the drain current and the linear region of MOSFET operation? ID equals to half mu1
Sir,
Cox.
option B, sir.
ID equals to half mu ox Cox W by L VGS minus VT square. ID equals to mu1 Cox W by L VGS minus VT into VDS minus half VDS square. ID equals to I naught E par Q VGS by KT. ID equals to Q ND mu n VDS.
Sir, first one for I think saturation region and second one for linear region.
That would be correct. So if you see, all four of these are current in some due to some particular in some particular cases. So this would be the current in a MOSFET linear region. This would be current in a MOSFET saturation region. This is also current in MOSFET. We will study this in later part. This is the current that is generally current in a metal or an ohmic region. So this is your basically conductance, you can say. ID equals to conductance into VDS. So now it's numerical base, small numerical. If the threshold voltage of a MOSFET is 0.8 volts and the gate voltage is 2 volts, what is the saturation drain voltage VD sat? 1.2 volts, 2 volts, 0.8 volts, 1 volt.
Sir, is this 1.2 volt?
That is correct. VD sat would be 1.2 volts. So VD sat is your VGS minus VT. So that is the condition for saturation region. So you can see VD sat is proportional to VGS. So if you increase VGS, your VD sat will also increase. So 2 minus 0.8 will be 1.2. So now another numerical. A MOSFET has an oxide capacitance Cox equals to 5 into 10 raised to minus 7 farad per centimeter square. Electron mobility mu n equals to 500 centimeter square per volt seconds. Channel width is W equals to 10 micrometer and channel length is L equals to 1 micron. With VGS equals to 2 volts, threshold voltage VT equals to 0.7 volts, and operating in the linear region at VDS equals to 0.08 volts, what is the approximate drain current ID? 150 microampere, 250 microampere, 500 microampere, 1 milliampere.
Sir, is this 250 milliampere? Microampere?
Yes, the answer would be 250 microamperes. So the formula, ID equals to mu and Cox W by L VGS minus VT VDS minus VDS square by 2. So you calculate this 1.3 and this whole thing would be 0.1008. This would be 10. Then this would be 2.5. Then you multiply everything. You will get around 252 microamperes. And that you can approximate to 250 microamperes. So now in the same device, what is the approximate maximum current for this device? 1 milliamperes, 2.1 milliamperes, 3.5 milliamperes, 4.7 milliamperes. What will be the maximum current you can get?
Option C, sir.
How did you reach option C?
Sir, can we back to the previous slide, sir? One minute, sir. Sir,
Yes.
last part, sir, you are multiply 0.08 with 1.3. Compute the bucket term, sir. Bracket term.
So instead of VDS, you're putting 1.3.
Okay, okay.
So when when will you get the maximum current? At what point can you get the maximum current?
Sir, when pinch off is occurs.
Yes. What happens after that?
After that, sir, there will be a channel will be closed, sir.
That is not true. Channel won't be closed. Channel will be saturated.
Oh, they are saturated.
So there won't be any more increase in current. So you will
Yes,
get a
sir.
constant current after that value.
Sir,
Yes.
when you compute mu n into Cox,
Yes.
so there will be a red word is there.
You ignore this you ignore that. Don't see, you do your own calculations using this.
Okay.
You have all the values here.
Okay. So, sir, I can find this by the help of saturation current ID equal to, then we can get the value, sir.
Yes, that is what you have to do actually. So uh, so the
No, sir.
maximum current will
I,
be your saturation current. So you will have to use the
yes, sir.
formulas.
Okay, sir. Half into mu n C of W by L VGS minus VT whole square. This is the formula, sir, I think.
Yes.
Okay, sir. I can do it, sir. 1 minute. Sir, is this 2.1 is coming, sir?
Yes. The answer will be 2.1. So if you
1 to
use,
5 actually.
yes, there will be some 2.111 something.
1 to 5, sir. Why am I also?
So, and you know how this formula comes, the saturation current formula. So if we see this formula, this is for a linear region, and you know at what when does what is the saturation point? When your VDS is equal to VGS minus VT. So if you
Yes, sir. Yes.
replace VGS by VGS minus VT, here it becomes VGS minus VT whole square minus half of VGS minus VT whole square. So you subtract it, it becomes VGS minus VT whole square by 2. So which is what you get here, VGS minus VT whole square by 2. So your saturation current formula is coming from a linear current formula.
Okay, sir.
So next question is, what is subthreshold conduction? Conduction where the channel is completely turned on, conduction before reaching strong inversion, conduction at very high voltages, conduction that occurs only in short channel devices.
Option B, sir.
That is correct. The answer would be conduction before reaching strong inversion. In the context of MOSFETs, what does the term subthreshold slope refer to? The angle of the output characteristics, the transition from off state to on state, the slope of the current voltage curve below the threshold voltage, the increase in gate voltage.
Sir, it is also, sir, B, sir.
The answer will be C. The slope of the current voltage curve below the threshold voltage. So if you plot your ID versus VGS, so at VGS below VT, you will see that it's not immediately zero. The current does not become zero immediately. There is some current you will find even at VT less than zero, and that current is known as your subthreshold slope. It's not that current. So if you take the slope of that curve between ID and VGS, that slope is our subthreshold slope.
Sir, can you explain one more time, sir?
I will do. Let's do two questions. After that, I will explain. So in the subthreshold region, the MOSFET current follows which dependency? Quadratic dependence on VGS, exponential dependence on VGS, linear dependence on VGS, no dependence on VGS.
Sir, exponential dependence, sir.
That is correct. The answer would be exponential dependence on VGS. And which factor increases subthreshold leakage in MOSFETs? Increasing threshold voltage, reducing drain source voltage, reducing channel length, using thicker oxide.
Sir, explain this kindly.
I will explain everything. So the answer to this is reducing channel length. So I had another question. I think it's so when I had showed you this, I had told you that this is also a formula that is related to MOSFETs. So ID equals to I naught E par Q VGS by KT is the current that you get in the subthreshold region. Is the so you can see it has an exponential dependence on VGS. So if you take log of this, you will get log ID equals to is proportional to Q is proportional to VGS. So VGS is proportional to log ID. So if you take the slope of that, that is your subthreshold slope. So if I plot, so like I showed you earlier, so in strong inversion, this would be high, this would be N type. But even when you are before inversion, there this would still be very low p doped. So it will still have some intrinsic or n type dependence. It won't be strongly n type. It will be weakly n type, or it will be intrinsic, or it will be weakly p type. So then also, if we if we give a current, there will still be some amount of electrons in this region, right? There will still be mobile electrons in this region. It won't be that very high, but there will still be some number of mobile electrons in this region. So if I give apply a voltage on my drain, I can still see some amount of conduction. It will be very low, but there will be still be some amount of conduction. So that conduction is called subthreshold conduction. And so if I am plotting,
Sir, before strong inversion,
yes,
the channel is channel has contained some amount of electron, so that if you apply drain to source voltage, there will be current is flow.
yes. So
It is called subthreshold.
in strong inversion, you have a very nice n-type channel formed. So we'll get a good amount of current. But even before the inversion is formed, there are like in extremely off condition, like in accumulation region, this region would be highly p type. There will be very less number of electrons available. But just before inversion, you will have a good amount of electrons here. Like it can be intrinsic or just above intrinsic, like very negatively negative, very small negative doped, or very less p doped. So there will be some amount of electrons, like 10 power 10 or 10 power 9 or 10 power 11 number of electrons. So you will have some amount of that can correspond to some conduction. You can still see some amount of current flowing through this channel. So if I plot in the linear part, so you will see my current goes like it's like this, and suddenly you will see an increase in current. So, and if you do like this, so this would be, you will find that this is what you call a threshold, your threshold VT. So this would be in linear region. But if I am plotting this same graph as log of ID, and this is VG, and this would be my VT. So above Vt I have a very high current, but below Vt also I will have a linear like this region. So it's so the dependence on Vg here is less. The dependence on Vg here is very high. It's a, so it's in log. So you can see the in log ID, this region is very flat, very linear region. So if I take the
Sir, this
slope,
region,
what
which region, sir, which is very high, dependent very high, sir?
this region, this is your sub threshold
Okay,
region. So sub threshold
okay,
means
okay,
below threshold.
okay.
So this is your threshold point. Below threshold, you will have a highly high dependence on Vg of your current but you won't be able to see that in your linear scale, because linear scale your on current is very high. So all your effect is hidden in your all that effect is hidden in very fine scale. So you have to go for log scale to see that, dependence, and you will see this type of curve. And if you take the slope of this curve like this would be like d of log d log id by dvg. That would be your subthreshold slope or subthreshold swing. Basically, subthreshold slope and subthreshold swing are inverse of each other. So if you're taking id upon vg or vg upon id, your subthreshold slope is vg upon id, log id. So next question: what is the significance of transconductance Gm in a MOSFET? It defines the current through the drain. It indicates the current gain of the transistor. It determines the threshold voltage. It affects the excite capacitance.
B, sir, option.
The answer to this would actually be it defines the current through the drain. So this is transconductance. So transconductance is basically the conductance that conductance of your drain channel. So basically how effectively your gate is able to model gate is able to give the gate is able to modulate your current in the on state. So now numerical, a MOSFET has an electron mobility of 500 centimeter square per volt second, an oxide capacitance Cox of 5 into 10 to minus 7 farad per centimeter square. Channel width to length ratio is 10. Gate gate VGS is 2 volts and VT is 1 volt. What is the transconductance of the device? 1 milliampere per volts, 2.5 milliampere per volts, 5 milliampere per volts, 10 milliampere per volts.
Sir, what is the formula of transconductance, sir?
So transconductance is
Uh,
your
explain this.
so transconductance is the conductance you get in from the transfer characteristics, which is ID versus VG. So transconductance would be the ID upon differentiation of ID and VGS. ID by VGS.
Sir, can you explain this?
So in the so transconductance is basically defining the conductance in from your conductance that you are getting from your ID VG curve in the on state of the transistor.
So, sir, it is a linear region operation, na? Formula will be derived from linear region, na?
So the current that is you are getting the it the transconductance formula won't change if you from linear or saturation. In both cases, your transconductance formula would be same.
Okay, okay.
Sir, how to derive?
So it's differentiation of ID and VGS.
The answer is, sir, 10 milliampere per volt.
The answer to this actually will be 2.5 milliampere per volts. I think I forgot to mention the so it's basically so if we take this formula, so it will be di by dvg. So basically, if you differentiate this with vg, so you will get so this all is constant. You will get 2 vgs minus vt. So you cancel 2 with 2. You cancel this 2 with this 2. So you will get mu n cox w by l vgs minus vt. So mu n would is your this is 500. This is 500. This is 5. This is 10. And this is 1. vgs minus vt is 1. And if you multiply all that, you will you will get 2.5 milliampere per volts.
Sir, 1 minute, sir, see the formula, sir.
So the formula would be mu n cox w by l and then vgs minus vt. Basically, you differentiate this by vgs.
The differential is equal to what, sir?
Sir, if I perform differentiation, we have got 2 VGS minus VT,
And
and
the two will cancel with the half.
okay, del I equal to then mu n Cox W by L VGS VGS minus VT.
Yes.
From that, I have to calculate del I by del VGS.
So all these values you have already been given. Mu1 you are given 500, Cox you are given 5 into 10 to the minus 7, W by L you are given 10, VGS you are given 2, VT you are given 1. So you multiply all that, you will get
But
2.5 milliamperes per volt.
sir, you said that GM will be del I by del VGS, na?
Yes.
But sir, if I perform, okay, sir. Okay, sir. Okay, sir. So mu n equal to, your problem is there, mu n equal to 500 and Cox equal to your 5 into 10 to the minus 7 and your W by L is 10
Yes.
and VGS is 2 minus 1. So we have got 2500 into 10 to the power minus 7 into 10. So 25000 into 10 to the minus 7. So we have got 5 milliampere. So 7, 3, 4.0025, 2.5 milliampere. Okay, sir.
Yes. So it will be 2.5 milliampere per volt, or you can
So
also
Sir,
this
del
come
I, del I by
this come to
del US. We,
25,000 into 10 to the minus 7 volt ampere per volt. Yes or no?
yes.
Okay,
And
okay.
ampere per volt is also written as Siemens S, which is the SI unit for
Okay.
conductance.
sir, here calculation is not done.
So your huh. So this is your formula for current at saturation: zero point 0.5 into mu1 into Cox into W by L into VGS minus VT whole square. So my transconductance is given as d of ID by d of VGS. So basically, so you know conductance is I by V. So transconductance you can calculate by dID by dVGS. And if I calculate that from here, so I will get, so these all are constant. So this I will calculate, then I will get 2 into VGS minus VT, and that 2 will cancel with this 0.5. So I will just get, so I will get this. And now here I will put 500 into 5 into 10 power minus 7 into 10 into 2 minus 1. So this would be 25,000 into 10 power minus 7 ampere per volts or Siemens. So that will become your 0.0025, which is your, so this is clear now.
Sir,
Transfer.
sir, hydrogen.
Yes, sir.
So next question, which I meant to show earlier. What is the primary reason for subthreshold conduction in a MOSFET? Thermionic emission over the barrier, band-to-band tunneling, diffusion of carriers in weak inversion, impact ionization.
Sir, option C, sir.
Yes, the answer would be diffusion of carriers in weak inversion. In a short channel MOSFET, what effect causes drain current to increase even in saturation? Channel length modulation, velocity saturation, avalanche breakdown, threshold voltage roll off.
Sir, is this channel the modulation?
This is answered with channel length modulation. So, so when you're increasing your drain current, it is affecting the channel. It is affecting the channel near the pinch off region, where the drain voltage drain region is connected to the channel. It is affecting the channel length there. But in a long channel, that modulation is not very significant, so it's ignored. But in short channel, that modulation is comparable to your channel length. So like if your modulation is in the order of like 1 to nanometers and our channel length is around 20 nanometer, 30 nanometer, so that 1 to nanometers is very significant there. So so that will affect the drain current, because in a shorter channel your current should be higher. Which of the following techniques is used to mitigate short channel effects in modern MOSFETs? Increasing channel doping, using high K dielectrics, reducing oxide thickness, all of the above.
Sir, option D, sir.
The answer would be all of the above. So all of these techniques can help in reducing the short channel effects. So if you
Sir, using high K direct.
so if you
This option, sir, option B is what happens? How it happens? Option B.
Sir, I think this question is that how we can reduce the short channel effect using high K directly.
yeah, so that's the next that is another question that I have here. In a short channel MOSFET, what is the effect of drain induced barrier lowering or double? Increases the threshold voltage, decreases the threshold voltage, reduces mobility, increases oxide capacitance.
Yes, sir.
Is the answer would be decreases the threshold voltage. So, what is the significance of high K dielectrics in MOSFET design? Reduces gate leakage current, improves subthreshold slope, increase drain source resistance, reduce carrier mobility.
Uh, high K direct.
Sir, is this improved subthreshold slope, sir?
No, the answer is here is reduce gate leakage current.
So explain this, sir.
So, which of the following helps mitigate short channel effects in modern MOSFETs? Using SOI silicon on insulator, increasing oxide thickness, reducing gate capacitance, reducing mobility.
Sir, using SOI, sir.
Yes, the answer is using SOI silicon on insulator. So now let's talk about short channel effects. This is how a transistor is. So if you increase the channel doping, your your in you will increase the amount of current that you are getting, and it will basically increase the barrier it will increase. So so how basically a MOSFET is typically used as a logic gate device, as a switch. So so this is your VG and this is your ID. So I take 2 points. One is VG equals to 0 and one at VG, like let's say VG equals to 2 or VG equals to 1 something, where my transistor is on. I take some point where my transistor is on, and I take so my VG. So what I want is to use it as a switch. I need two states: a low current state and a high current state. And there should be significant difference between low current state and high current state, between off state and on state. So my off state is at VG equals to 0 and my on state is at VG equals to 2. Let's assume by some reason my threshold voltage got decreased. So what will happen is, instead of my threshold being here, it will reach somewhere here and it will go like this. Instead of, so earlier my threshold was here, now my threshold has decreased and it has reached. But you see, due to this value, my current at VG equals to 0 has increased significantly. This is log of ID. This is log of ID. So you see how this is several orders of magnitude increase due to a small change in my VG. I have several orders of magnitude increase in my off current. So reducing VG, I don't want to reduce my threshold voltage. So, but due to double and other effects, my threshold voltage is decreasing. So that is a reason. So why, first of all, why we want to go short channel? So we want to put as many transistors as much possible. So we want the transistor to be
Packaging basically.
smaller and smaller. So we want to
Yes,
reduce
sir.
the channel length for that. But
Okay, sir.
due to that, I am getting double. Basically, my because of getting a short channel, like say small channel, because when I put, because of my drain, so it affects this region, and so now my effect of drain is going towards the whole channel region. So it is giving me multiple short channel effects. Also, if I if my channel length is too small but my oxide thickness is too high, I won't have enough field effect. Like my oxide thickness is this much and my channel is this much, I won't be able to get proper field effect. So my so my Cox, so I want to increase my Cox also to increase my field effect. And you know, Cox is epsilon by T.
Yeah.
Epsilon by Tox. So so, what are the ways to increase Cox?
Either epsilon increase or P of decrease.
Yes. So either I increase my epsilon ox or my decrease my Tox. But if I decrease my Tox too much, then I also get gate leakage currents, because if my Tox is too small, electron can just tunnel through the gate oxide. Like
Yes, sir.
1 to nanometers. If my Tox is 1 to nanometers, my electrons will start tunneling through the gate, and I will have a huge gate leakage problem. So I don't want that. So my other option is to increase my epsilon ox. and that is why we go for high K dielectrics. So
Okay, sir.
that is why we go for high K dielectrics, so that we don't have to decrease our TOX too much.
Okay, sir. Okay.
And now another, and what a silicon or insulator is basically, this is my substrate. I grow an oxide layer above it, and then I deposit. So this is my silicon. I grow SiO2 on it, and then I grow another very small layer of silicon here, and then I form my source and drain on this part. So this is called silicon on insulator. So what you have here is so your silicon itself is very thin. So now what will happen is, so your p-type charges that were so here this whole region is p-type, only this part is n-type. So you have this so you have a huge effect of this p-type region on this n-type region. So so you but here that so here you have the only very small thickness of channel, so you can convert this whole channel to your n-type. You can create this, and you have very less amount of hole, then you will have very less amount of holes present from your substrate. So you will have very good it will it will improve your gate control very much. So another reason that you won't have to decrease your TOX too much, because now we don't need very high COX to have field effect. So that is why we use silicon on insulator. And the next question, what is the primary effect of applying a negative substrate bias VBS in an N-channel MOSFET? Decreases the threshold voltage VT, increases the threshold voltage VT, reduces short channel effects, increases the oxide capacitance.
Option C, sir.
Increase threshold voltage, sir.
That is correct. It will increase the threshold voltage. So basically, what it means is, so here, so this sub, I have a, so in a in a N channel MOSFET, my substrate is P type. So so if I'm applying a negative bias to this part, this substrate, it is affecting my MOS characteristics, and it will increase my threshold voltage. So that is also another way to mitigate my decrease in threshold voltage effect. But by applying a voltage on my substrate, I am increasing the power consumption also. So this is what we call body effect, where my gate voltage is dependent on my body also. So in typical operation, my source and body both are grounded. So next question. A MOSFET has an oxide capacitance of 4 into 10 to the minus 7 farad per centimeter square and a depletion capacitance of 8 into 10 to the minus 8 farad per centimeter square. What is its subthreshold swing factor N? 1.0, 1.2, 1.5, 2.0.
Sir, subthreshold swing means VG by log ID, na?
So this is not subthreshold swing. This is subthreshold swing factor.
Okay, okay, okay.
So it determines how my subthreshold swing is changing.
What is the formula, sir?
Yeah. So the formula for this is 1 plus C depletion by C ox.
Yes, sir.
1.2.
Yeah. So the answer would be 1.2. So this is 0.8 into 10 to the minus 7 divided by 4 into 10 to the minus 7. 0.8 by 4 is 0.2 and 1 plus 0.2 is 1.2. So subthreshold swing factor N is 1.2 and the ideal case for ideal case N is 1. So you will understand this in this question. For a
So, sir,
MOS
so, sir,
so for a MOSFET operating in the subthreshold region, if the subthreshold swing S is 90 millivolt per decade, what is the body factor N? Which is what subthreshold swing factor or body factor N? 1.3, 1.5, 1.8, 2.0.
we have some block terms here.
So do you know what is the subthreshold swing S for ideal case?
One, sir.
Not N, S. Subthreshold swing in ideal case. Here it is given as 90 millivolts per decade. What is in the ideal case?
Answer.
Don't know, sir. Don't know.
So the answer to this would be 1.5. So S is given by N KT by Q ln 10. And so at room temperature, you will have KT by Q as like 25 or 26
0.026.
26 millielectron volts. As you have given here 90 millivolts per decade and ln 10 is a 2.3. So that comes out to be 1.5. Yeah. So so your in subthreshold region we studied that my I is given as I naught e power q vg by kt. If I take log of this, I will get log of I is equal to log of I naught. I will ignore log of I naught plus this term. I will ignore log of I naught for now, and this would be Vg by
Q into Vg by Kt.
yeah. So Vg by Kt by Q, and so this is in E, but this is log in terms of in base 10. So log in base 10 would be 1 upon. So this was in E. So if I have to convert in base 10, so I will have to add 1 upon ln 10. So if I take this here, I will get my Vg by log I is equal to Kt by Q ln 10. So I will get Vg by log I Kt by Q ln 10. So this is the ideal case. In ideal case, so Vg by log I is what you get as S, which is sub-threshold swing. This is Vg by log I means sub-threshold swing. So 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 when will log I be 1? In what case my log I is 1?
10, 10,
10.
10.
Yes. So
Ideal substitute swing will be 10, sir.
no, the ideal sub-threshold swing is not 10. So ideal sub-threshold swing is my Kt by Q. So Kt by Q is at room temperature is 26 and ln 10 is my
3 volts.
2.3. If you multiply this, you will get 60. So this is log I. So basically, and it is in powers of 10. So that is why we write it as this would be 60 millivolt per decade. So what does per decade means? That at every 60 millivolts, I will have one magnitude change in my current. So like if at 60 millivolts my current is say 1 nanoamperes, at 120 millivolts my current would be 10 nanoamperes. At 180 millivolt my current would be 100 nanoamperes. So
Okay, sir.
after every 60 millivolts my current is getting multiplied by 10. So that is why we say per decade. So it means after this point my current is getting multiplied by 10. So this is the ideal case. But in non-ideal case, you multiply an n with it. And because of this n, your subthreshold slope decreases. So basically subthreshold swing is increasing means subthreshold slope is decreasing. Subthreshold slope is inverse of subthreshold swing. So my subthreshold swing, if I put n equals to 1.5, my subthreshold swing is 90. So ideally, you want your subthreshold swing to be as low as possible. But At room temperature, the thermodynamic limit is 60 millivolts per decade. So basically, if this is my VT, let's say this is my ideal case. So if my subthreshold swing is 90, I will get something like this. So my current at zero is increasing. So I want this to decrease as much as possible. I want it to be as steep as possible. But by thermodynamic limit, it cannot be below 60 millivolt per decade. So if but there is one way to go below 60 millivolts per decade, and that is tunneling. So
I
so nowadays there are research going on and looking into tunneling channels where your conduction is through tunneling, because tunneling is restricted by quantum limits, not thermodynamic limits. So by tunneling you can have a subthreshold swing less than 60 millivolt per decade also. So this is what I had for today. Thank you.
sir,
Yes, sir.
one time, sir, for the last slide, sir.
Yes.
Can you explain, sir, the relation between successful swing and your swing factor? You have said that if we reduce the swing, successful swing, factor will be. So there is a relation between successful swing and factor, sir.
Yeah. So this is so like I sure factor n is given by 1 plus c dep by c ox.
Okay.
So ideally your depletion, so you want ideally your depletion capacitance should be zero, but obviously in real case depletion capacitance will never be zero.
Yes, sir.
So you will always have n greater than 1.
Yes, sir.
So your subthreshold swing is given by n kt by q ln 10. So kt by q ln 10 is equal to 60 millivolts per decade for at room temperature
Yes, sir.
at 300 Kelvin. So at 300
Yes,
Kelvin,
sir.
kt by q ln 10 is 60 millivolts per decade.
Yes, sir.
So if you multiply anything greater than 1 to it, it will obviously increase. It, like in this case, if you multiply 1.5, it goes to 90 millivolts per decade.
Yes, sir.
Yes. So let's say my on current at threshold is, let's say it's 1 milliamperes, let's say, and my VT is, let's say, 540 millivolts. Okay.
Okay, sir.
So my VT is 540 millivolts and my on current at VT is 1 milliamperes. Okay. So now I have
Okay,
to
sir.
calculate the current. What will be my current when VG is 0? What will be the current when VG is 0? How will you calculate that?
Less, less than, sir, 1 milliampere.
What?
Less than 1 milliampere now.
I want exact value. I want
At
exact
0.
value of current when my VG is 0.
I equal to 1, sir. No.
No, it will definitely be below 1 milliamperes.
Obviously below 1 milliampere.
So what will be the value?
Sir, 0, sir.
It won't be 0.
0, sir.
It will not be 0.
Okay. Sir, please tell me, sir.
Yes, so you see, so your subthreshold swing S is given as 90 millivolts per decade. So for every, if I start from my VT and start reducing, so after every 90 millivolts, my current will reduce by one order of magnitude. It will be
Okay,
divided
okay,
by
okay.
10. Okay.
Okay, 6 times divided by point 0, 6 times divided by 1 milliampere.
Yeah. So if you go from 1 milliamperes and you go 6 times, you will end up at 1 nanoamperes.
1 nanoampere, yes, yes, 1 nanoampere, yes.
That is if my S equals to 90. At S equals to 90, it's giving 1 nanoampere. At S equals to 60, what will I get? If my subthreshold swing is 60,
1.5.
0.01, point 1 nanoampere,
no, I will get
point 1,
I will get 1 picoamperes.
yes, yes, 1 picoampere, sir, 1 picoampere.
So you see the difference here. It's 3 orders of magnitude.
Yes, sir, yes, sir.
Yes. So I want the current at VG equals to 0 to be as low as possible, because that is called at VG equal to 0 is your off state. You get it?
Yes, sir.
It's supposed to be off state. So
Yes, sir.
let's say there is some processor in your computer and you are not doing anything. That means the processor should be in the off state, right?
Yes, sir.
Let's say there are 1 billion processors in your device, and each of that is giving 1 picoampere current, and in other case each of that is giving 1 nanoampere current. That is the current they are leaking in the off state, right?
Yes, sir. Yes, sir. So this is the as low as possible. This will be good set of region.
Yes, but the thermodynamic limit is it can't go below 60 millivolt per decade. But in reality,
Okay.
getting 60 millivolt is per decade is very challenging.
Okay. So, sir, we have to go beyond 60 limit. 60. Uh, in sir, 1 nanoampere below 1 nanoampere, sir. What are the methods, sir? We have to follow.
Yeah, so that is why so see we so when we are when so I we want our transistor to be as small as possible, but when we are making it smaller, my depletion capacitance is increasing because
Yes,
of
sir.
short channel effects. So I want to increase my Cox also. So I want my N to be as
Yes.
close to 1 as possible. So I want to increase my Cox. So that is why we are either reducing the channel, the gate oxide thickness, or we are using high K dielectrics.
I can identify. Yes.
So the whole point of optimization of all these short channel effects mitigation is to reduce my off current at Vch equals to 0 to minimum.
Okay. Okay, sir. Okay.
The the whole story here is that I want to have this number to be as low as possible. So I want this number to be as low as possible and this number to be as high as possible. So when
Okay, sir. Okay.
at on I want very high current, at off I want very low current.
Okay, sir.
That is the whole story, that we are doing so much optimization to reduce while reducing our transistor size. Okay, thank you. Any other doubt?
Thank
Sir,
you,
your
sir.
class will be again in next Sunday, na?
Yes, next
Okay, sir.
next class will be next Sunday.
Okay, sir. Thank you, sir. Good night, sir.
All right.
you.